As important as it is to know and explore what the potential of this technology is, it is equally important to understand what the hurdles are. What is holding this technology back from universal implementation in the future? Talking to experts, this video will dive not only into some of the more practical and financial challenges, but also some that arise inherently from using the technology in natural systems. One of the significant challenges in implementing digital twins in life sciences is understanding the natural system's level of detail and complexity. A digital twin must capture an appropriate level of detail to be useful. This requirement raises the question, what level of detail is necessary to make these systems effective? This is also a question asked in the Tomato project, something Joachim worked on.
So we've been trying to find out at what level do you need to represent those tomato plants, for example, and understand how they grow and how they function in order for this digital twin to be functional. You can go all the way to the genes and the products and the metabolites and the hormones and everything, but the question is, do you really need that in order to efficiently predict tomato performance and yield and resource use efficiency? Probably not. But a two-course description of how tomatoes grow, how tomato plants grow and produce is probably also not good enough. What we do realize is that you need to have the processes in place there that are responsible for the growth of the fruit and of course the plants in general. So things like photosynthesis, water use and stuff like this. So a mechanistic model that allows you to predict how well tomato plants do, taking into account the greenhouse environment and the variables there, and the feedback between environment and the crop.
Determining the right level of detail is a balancing act. As Joachim pointed out, the right balance of detail will differ for every application. What works for one biological system may not be suitable for another, making it a complex case-by-case decision. Another level of complexity is introduced by the feedback mechanism in digital twins. Higher complexity in the model often means longer simulation times, which can be a significant drawback when timely results are needed.
We want to do a range of simulations every day in order to see how to update your crop again the next day. You need your simulations to be done relatively quickly in order to do enough of them to say something sensible on how to further manage your crop, right? So there you need some level of model performance in terms of speed that allows it to be part of a digital twin.
A critical challenge in developing digital twins is determining what data is essential to collect. For a digital twin to be both complete and beneficial, it must be built on the right data. However, knowing what data to collect isn't always straightforward.
That's also the whole idea about what we're doing, trying to make the data complete. I always challenge guys from Wageningen, tell me what you need for your model, and I'm going to try to automate it.
One of the key tasks in creating a digital twin is identifying what parameters are necessary for accurate modeling.
Yeah, we all have that, but you miss that. That's what I want to learn. That's what I want to know from Wageningen. What parameter do you need to train your model that I'm not delivering you?
Joachim also faces similar challenges in his work, emphasizing the need to determine precisely what data is necessary to create a functional digital twin.
What we wanted to find out is what do you need, right? And how easy is it? So there's a couple of things there. First of all, in order to constantly update such a digital twin with data coming from the actual twin, you need sensors, right? So you need to be able to monitor the crop and its environment as it's growing and developing. So you need sensor equipment in order to get that data. Otherwise, you cannot feed the model with updated data. And this sensor technology, I mean, it's developing incredibly quickly. But the type of sensors that we've been using within this research project is not the type of sensors that growers typically have lying around in their greenhouses, right? So one thing that we definitely are going to need is a good overview of what is the minimum number of low-cost sensors that are easily accessible and available that we need in order to make such a twin work, right?
Joachim's perspective reinforces the idea that knowing what data to sense is a collaborative and evolving process. One of the greatest challenges in implementing digital twins in agricultural settings is the need to acquire vast amounts of data. This requires advanced sensor technology capable of capturing detailed information across large areas.
Every week we have 2 satellite images of biomass, 2 satellite images of temperature. We have weather stations all over the place. Just think about how many data points you could catch. We know the GPS location from every tuber, we know the yield, we know biomass, we know irrigation. Everything you can measure is fed into this database.
This comprehensive data collection forms the foundation of a digital twin, but managing and integrating these diverse data sources is a significant challenge. One of the critical hurdles is getting these data points to work together in an integrated system. Currently, many data sources are not connected and communicate in different data sets and languages.
So none of them are connected to each other. All of them are talking in different data sets in different languages.
Fortunately, there are ongoing efforts to implement data standardization, which is starting to allow for greater integration. High-quality, comprehensive data is essential for creating effective digital twins. However, data in the life science field can be incomplete, inconsistent, or inaccessible due to privacy regulations and propriety concerns. Overcoming these data issues requires robust data governance frameworks and collaboration across institutions, which can be difficult to establish and maintain. One of the key challenges in making digital twin technology accessible is the paradox of investment. Precision agriculture, a prime application of digital twins, is incredibly expensive and requires significant investments.
But the biggest issue for adoption is that the guys that will invest are already high up, and they will not have the benefits of the guys that are there.
Jakob highlights a major issue. The individuals and organizations capable of investing in this technology are already at the top of the agricultural sector. These high-level players have the capital and knowledge to implement digital twins, but may not see as substantial benefits compared to those lower in the hierarchy who cannot afford the investment. This paradox means that only the richest players in agriculture, who are already highly efficient, will invest in digital twins. To combat this, efforts must be made to make this technology more accessible through the use of affordable sensors and cost-effective solutions. Developing affordable sensors and lowering the overall cost of implementation can help democratize access to digital twin technology, ensuring that smaller farms and less wealthy institutions can also benefit from these advancements. Another aspect of accessibility is ensuring that digital twin technology can be used by non-scientists. The output generated by digital twins should be understandable and actionable for a broader audience, not just experts.
The output, so the kinds of things that the twin produces, the information that a grower can potentially use in order to optimize the system needs to be understandable. In this research project, the digital twin was really very much a scientific tool still, and we would like, of course, at some point to get into the situation where the twin is and the output of the twin can be used, can be managed by anyone, and the output can be interpreted by anyone.
Visualization plays a role in making digital twin technology more accessible. Tools and interfaces that simplify complex data can help users from various backgrounds understand and act on the insights provided by the twins. Efforts at Wageningen University, for example, are focused on developing visualization tools that make it easier for non-experts to interact with and benefit from digital twin technology. These tools can bridge the gap between complex scientific data and practical actionable insights. Natural biological systems are inherently variable and subject to many unpredictable factors. Capturing this variability accurately in a digital twin is one of the most significant challenges.
If you build a digital twin for a plane, an airplane, that's complex, but we know how the plane works, right? Because we built the plane ourselves. We have a good idea of the physics that govern the functioning of a plane or any other, man-made device that you may want to twin. Which doesn't make it easy. It's still pretty complex, but at least you're not dealing with as many uncertainties as you do with living organisms like plants. And this is, I think, one of the major challenges in making digital twins for agricultural or horticultural systems is the variation that you get dealing with living organisms and the uncertainty that you're confronted with in terms of how will they grow and how do they do, right?
And like mechanical systems, biological systems cannot easily be controlled or predicted. This uncertainty must be understood and incorporated into the digital twin. Models must be sophisticated enough to account for the individual differences and the dynamic nature of biological processes.
To deal with that is, well, at least one of the ways to go about that is to make sure that the measurements that you do in order to design and update the model as you go is done with a high sample size, right? You're dealing with a variation in your crop, so it means that you need your sensors in different locations in the crop, and you combine all that data in order to make sure that the variation that you capture is indeed the variation that you find in your crop, and that then goes into the model.
Joachim emphasizes that dealing with biological variability involves working with the inherent uncertainty rather than trying to eliminate it. Continuous refinement and validation of the models are essential to ensure they remain accurate and useful. As you can see, there are multiple challenges in implementing digital twins. With all these challenges in mind, we can look to the future and see how these challenges can be overcome and where the technology is headed. Thank you for watching this video, and we hope to see you next week.